Hey everybody, welcome back. Today we're going to be starting a new unit called exponential functions. Now the functions that we've talked about so far this year, we've talked about linear functions, quadratic functions, and now exponential functions. So exponential functions you've actually seen a little bit, or you've seen something very similar when we were in our sequences unit. So exponential functions and geometric sequences have a lot in common. You will notice that the formula for exponential functions, so this formula right here, hang on. For some unknown reason, it wasn't writing for me. There we go. All right, so you'll notice that this formula here is very similar to the explicit form. For geometric sequences, we're just using some different variables to represent different values. So A in this case is the initial value. Remember, initial value goes along with our y-intercept, and that's where our graph crosses or touches the y-axis. And B is what represents our growth or decay factor. Okay, so you'll either see our graph growing or increasing. So as our x values increase, our y values increase. Or you'll notice as our x values increase, our y values will decrease, and that's what we call our decay factor. Now, exponential functions are actually something that we could use to describe really what's going on in the world right now. So there are a lot of real-world aspects or real-world connections with exponential functions. You'll notice when you hear things such as the price doubles, or the size doubles or triples, or is cut in half. These are all ways that we could describe different types of exponential functions really in the real world. So we're going to take more of a look at that in a couple days, but I just wanted to give you a little introduction there. How do we recognize an exponential function? Well, the independent variable, or our x value, so the x value is the exponent. That's how we can recognize an exponential function compared to maybe a linear or quadratic. The base that our x value is attached to is a constant, so just keep that in mind as well. So the base is a constant. Okay. So if we're looking at these three examples down below, when I look at y equals 3x plus 5, I immediately see slope-intercept form, y equals mx plus b. And slope-intercept form goes along with linear functions. Each exponent attached to x and y is a 1, so that's another way for us to remember that this is a linear function. Y equals negative 4x squared plus 8x minus 16. This is standard form for a quadratic. Look at this x squared right here. That squared, or that exponent of 2, tells us this is a quadratic, because 2 is the largest exponent we see. And finally, y equals 2 to the x power. When we have an exponent that is a variable, when it's an x, we know that this is going to be an exponential function. And notice how the base, that 2, is a constant. All right, let's take a look at some graphing. So if we were to graph this, so hopefully if you don't have a calculator handy, that's okay, just follow along. If you do have the internet, you can go to desmos.com, that's DESMOS, and that's actually a graphing calculator that you can use right from your computer. So I don't know if that might help people. So we're going to graph this function. Notice that this is function notation because it uses f of x instead of y equals. So don't be confused there. This is still the same form we were working with above. Now we've just put in some values instead. So going back to that initial value, remember we said A represented our initial value. Now A here is 1. So if you look, the A and the 1, I'm trying to do this the best I can here without making it look too scattered. So A and 1 are the same. So our initial value or our y-intercept is 1. So our y-intercept equals 1. So remember, our y-intercept would be at the point 0, 1. It has an x value of 0, a y value of 1. Now I'm going to put the y-intercept right in the middle of my table. This is one point that I am going to be graphing. And I'm actually going to choose points that kind of are right really close to this x value of 0. So some other points I might put in are like -1 and -2, 1 and 2. Now you can find the corresponding y values by hand. Remember, the x values we can pick because they're the independent variable. The y values depend on that x value that we choose. So if you want to do all these by hand, you are welcome to. Remember that you have to apply the exponent before you multiply. So in this case, like let's say I put an x value of 2 in, I would have to take, so f of 2 is 1 times 2 raised to the second power. According to PEMDAS, I'm going to take 2 and I'm going to square it. So 2 squared is 4. And then I multiply that by 1. So you are welcome to do these by hand. I actually went to my calculator and I plugged in the function 1 times 2 to the x power. And then I went to my table right where 0, 1 is located, and I was able to get the rest of the points that I needed to fill in my table. Now don't be nervous, so I'm just going to fill in the values that I got here. Now don't be nervous when you see these decimals. That's okay. We want to plot those too because we want to see the trend of where our graph is going. So if I just start plotting my points here, I get 0, 1, -1.5, -2.25. We're just going to kind of guesstimate here. 1, 2, 2, 4. And you know what? Just because I think I can squeeze it on my graph, I'm actually going to go out one more because according to my table, 3, 8 comes next, and I can definitely fit that on my graph. Anybody from my class knows I love to fill in my graph as much as possible. Okay, so if you were to actually look at this function, so if you were to look at the graph of this function, you will notice that it curves. Okay. Now with exponential functions, you'll notice that our y values start to increase at a pretty rapid pace. So it's not a constant rate of change like with linear functions. You'll notice the difference in your y values. Let's see, first we go up by 0.25, then by 0.5, then by 2, then by 4, then by, you'll see that we're not increasing by the same amount, but instead, if you kind of look at our y values, you'll notice that there's actually a common ratio. So we're multiplying by the same amount each time to get from one y value to the next. And in this case, it looks like we're multiplying by 2 to get from one y value to the next. Okay, so that's coming in a little bit later, but looking at our graph, you'll see reading it from left to right, we are increasing. Our graph is curving upward. So as our x values get larger, so do our y values. What is the domain of this function? Well, you'll notice we can basically keep this graph going from -infinity to +infinity as far as our x values go. We can pick any x value we want. It will fall somewhere on our graph. What is the range? So this is really interesting. You'll notice that our graph never actually crosses over. We never have any y values that are negative. So we never cross over that x-axis here. And we also never actually touch 0. We never, ever, ever touch a value of 0. If you go to your calculator and you look at your table and you keep looking at x values that are further and further in the negative direction, -2, -3, -4, -5, you will notice that your y value is going to get so unbelievably small, but it's never actually going to be 0, ever. That's because there's no value we can plug in for x as an exponent that's going to allow us to get a y value of 0. So we come dangerously close to 0, but we never actually touch it. So in this case, our range is going to be any y values greater than 0. So that would be just one notation that you can use. If you want to use interval notation, we could say from 0. Remember, we would use a parentheses because we're never actually touching it. But our y values do increase at a pretty rapid pace, and they are going to go up to infinity. So the idea of us getting really, really close to 0 but not actually touching a y value of 0 is pretty special in this case because it's called an asymptote. Now, I say this wrong every single time. I've had previous math classes that just laugh at me because I love to put additional syllables in there, so bear with me. But an asymptote, it's a line that a graph gets closer and closer to, but never touches or crosses it. So in this case, if we are looking at what the asymptote is for our particular graph, in this case, we get awfully close to the line. Now, in this case, we're going to look at it being a horizontal line here, because again, it's going to be a y value. So we're looking at when y equals 0. So that horizontal line when y equals 0, that's technically the x-axis. But we get dangerously close to that, but we never actually touch it. So this is a line. It's called an asymptote, and you'll see that with exponential functions. There's always going to be a line that we're going to get super close to but never actually touch. So in that case too, let's keep going. Do we have any x-intercepts? No, we do not. There are none here. We do not cross or touch the x-axis at all. Do we have a y-intercept? Yes, we do, at 0, 1. Or you could say y equals 1. That's fine too. Where is the graph increasing? Well, if you notice, again, when we think about increasing or decreasing, we're looking to see, as our x values get larger, where are our y values also getting larger? And really, that's taking place throughout the entire graph. Our whole graph is increasing here. So when is the graph increasing? Remember, we're talking about over what x values? From negative infinity to infinity, our graph is always increasing. Is our graph ever decreasing? Not in this case. Are we showing a growth or decay? Well, we're showing a growth because, again, like I said, as our x values are increasing, our y values are also increasing. So this is what we would call a growth. Okay, as our x values increase, our y value also increases. All right, let's keep going to the next page. Okay, so let's graph this function now. So again, the first thing, if we can identify A, that'll help us with starting out our table. So I'm just going to write the general form underneath for a second so I can pinpoint what represents A, what represents B. So A looks to be 1, B looks to be 0.5. That's our growth or decay factor. So with our A value of 1, that means we have a y-intercept at 1, or we could say as a point, it's 0, 1. Okay, so right in the middle here, 0, 1. Now I'm gonna, and again, you could do this by hand, you are welcome to. I'm gonna go ahead and go to my calculator, and I'm gonna type in this function into my calculator, so 1, and I'm gonna type it in exactly as it looks, parentheses, 0.5, close that parentheses, raise it to the power of x, and then I'm going to take a quick peek at the table just so I can fill in the remaining values for the table that I have created here. So I'm going to once again stay pretty close to my y-intercept because that gives me a pretty clear picture of what's happening with my graph. So you can see very similar values to what we saw in our previous function, except our y values kind of switch space, switch places. So our y values now look to be getting bigger as our x values are getting smaller. So let's go ahead and graph this. We'll just see what this looks like. Okay, and I'm also going to include, just because I can fit it, I notice negative 3, 8 comes next, so I'm actually going to include that one on here too, again, just to give me a really good picture of this graph. And then I'm going to connect my dots from left to right. Ooh, again, hopefully yours looks a little nicer than mine. And you'll notice once again, so if you keep going with your x values towards the positive value, so like x equals 3, x equals 4, when x equals 5, if you keep going in that direction, you're going to notice that our our y value is going to get smaller and smaller and smaller and smaller, but it's never, never, never going to be 0. So what is the domain of our function? What x values are we allowed to plug in? We can plug in any x values we want. So from negative infinity to infinity, or we could say all real numbers. What is our range? Okay, our range, our y value. So again, our y value will never ever be 0. It's going to get really close to it. It's never actually going to touch it. But our y values are going to be anything greater than 0. So we could say y is greater than 0, or we could write from 0 to infinity. Okay, but our y value will never actually touch 0. It's going to get super, super close to it, but it's never actually going to touch it. Do we have any x-intercepts here? Nope. We're never crossing or touching the x-axis. What's the y-intercept? Well, our y-intercept here is 0, 1. Okay. And where is our graph increasing? Remember, to answer this question, let's read our graph from left to right. So if I'm looking at my graph from left to right, as my x values get larger, are my y values ever getting larger too? No, that's never the case. In fact, with this graph here, as our x values get bigger, our y values are always getting smaller. So in this case, we're never increasing. We're always decreasing. And over what x values will we be decreasing? All of them. So from left to right, you'll notice our graph is in a downward curve the entire time. So our graph is always decreasing. Are we showing an exponential growth or decay? So this would be a decay. And because, as we just mentioned, as x increases, y decreases. And that's why we have a decay. Okay, all right, so just continuing on here, because this is kind of a long notes and I don't want to keep you guys too long. Where will I ever use this? So again, a ton of real world applications. Obviously what we're seeing now with the coronavirus is very much, you know, an exponential type function. So there's definitely a lot of things that you can, a lot of areas that you will see exponential functions in the real world. This is just a list of a couple of them. Again, we'll get into more of these later on in this unit. So if we're looking back at example 1, so take a second and flip back to example 1. What was the b value? All right, so looking at example 1, the b value, so if I'm looking a times b raised to the x, so that's the constant that our exponent of x is attached to. In example 1, b is 2. And this graph represented a growth. Okay, so now when I take a look at example 2 and I again find what b was, b in example 2 is 0.5. And we said that this graph represented a decay because as our x values increased, our y values decreased. All right, so let's come up with a rule here. When b is less than 1, the graph decreases. So less than 1 is looking at example 2. All right, so we notice that when the b value is less than 1, our graph decreases. And this means it's an exponential decay. So this is always going to be the case. And I'm going to make this just a little bit different. So when b is less than 1, we'll say when b is between 0 and 1, because it's very rare that you see a negative b, but just in case. So when b is between 0 and 1, we call this a decreasing function and it's an exponential decay. When b is greater than 1, like in example 1 from the front of your notes, then we're going to say the graph is increasing, or it increases. and that means it's an exponential growth. All right, so one thing I want you to notice is this b value is very significant when it comes to the change that occurs with our y values with respect to each increase in x. So if you look back at example 1, and if you look at your table, what do you notice is happening with your y values? Remember, this is not a constant rate of change. Think back to geometric sequences and that common ratio where our y values changed by multiplying each y value by a certain amount to get from one value to the next. If you look at example 1, with each increase in x, our y values double, or we multiply our y values by 2, which makes sense because the b value is 2, and that is our growth or decay factor. Now take a look at example 2. What do you notice is happening to the y values? They're being cut in half with each increase in x. This makes sense because its b value is 0.5. This is the decay factor. This is what's happening with each increase in x. Our y values are being cut in half. So that b value is very significant. If we think back to geometric sequences, this is kind of like our common ratio. It's what we're going to be multiplying each y value by to get from one to the next with our increase in x. So just wanted to point that out before we went too far ahead. All right, so now let's take a look. We're going to go down in our notes a little bit more here. Let's work with that b value. Let's make sure we can identify based on what b is if we have a growth decay or a growth, I'm sorry, an exponential growth or an exponential decay. Whew, it's been a while. All right, so looking at our first equation, y equals 50 times 4 raised to the power of x, I can see that my b value is 4, which means I have an exponential growth because my b value is greater than 1. If I look at number 2, I get y equals 2 times 0.25 raised to the power of x. I can see that my b value is 0.25. Seeing that b is between 0 and 1, this is going to give me an exponential decay. As my x values increase, my y values are going to decrease. So now we're going to take a closer look at our growth and decay factor. And we're going to talk about how the growth and decay factor is affected by a percent rate of change. So the percent rate of change is this r value. So you'll see two formulas down below. Y equals a times 1 plus r raised to the power of x, and y equals a times 1 minus r raised to the power of x. So these are specific formulas that represent exponential growth and exponential decay. So you'll notice the difference between these two formulas and our standard form, or the form that we were using at the beginning of the notes, is b is kind of missing. B is actually broken down into 1 plus r and 1 minus r. So this is really where b comes from. How does that b value get created? So this r value is our rate of change as a decimal. So how are our y values changing based on each increase with x? That's pretty much what we're going to be finding out here. So what we're going to do is we're going to look at the next bunch of examples, looks about 6 of them, and we're going to determine if the graph shows a growth or decay. Again, we're going to really focus on that b value. And then we're going to give the percent of increase or decrease from the time period. So how are we noticing these y values are growing or decaying? So let's take a look at example number 1. Y equals 4 times 1.2 raised to the power of x. So if I'm looking at this, I'm noticing that my b value is 1.2. That tells me this is a growth because it's greater than 1. My growth or decay factor is what that b value is in the problem. So this is asking us basically just to write down what the b value is. And our b value in this case is 1.2. It's making sure we know how to identify which one is b. So what's the percent change? How are we noticing our y value is changing here? So if I look at this, I'm going to go to my exponential growth formula, and I'm going to see that to find b, or to really create b, I take 1 plus r, which is my rate of change, and I should come up with that b value. This is how b is created. Okay, so knowing that b is 1.2, I'm just going to plug in things that I know, and now I'm going to solve for r. I'm going to solve for this rate of change. How is our y value changing? And in this case, as a decimal. So I'm going to subtract 1, and I get r equals 0.2. Now I'm going to turn this into a percent because I want to know the percent of change that's taking place versus the rate of change as a decimal. So to turn this into a percent, I'm going to multiply by 100, and I get 20%. Now, seeing that this is an exponential growth, we're looking at a 20% increase in each y value with every increase of x. So there's a 20% increase in our y values with each change in x. That's what we would notice if we were to create a table here. Our y values would grow by 20% with each change in x. Now let's take a look at number 2. Y equals 3 times 0.25 raised to the power of x. Our b value is 0.25. Seeing as that's in between 0 and 1, we would call this a decay. Our decay factor is what the actual b value is, which is 0.25. Our percent change. Okay, so how are our y values changing as a percentage? So once again, I'm going to take a look at my formulas above. I'm actually going to use the exponential decay formula here, and I'm going to say 1 minus r should give me my b value of 0.25. So thinking about this, what do I subtract from 1 to get 0.25? Oh, I subtract 0.75, so that must be what r is, 0.75. Now to put this as a percent, or to make this into a percent, I'm going to multiply 0.75 times 100, and that gives me 75%. Now looking at this, this is a decay, so this is going to be a 75% decrease in my y values. So with each increase in x, my y value is going to decrease by 75% each time. That's what this is telling me right here. All right, let's keep going. So number 3, y equals 8 times 1/2 raised to the power of x. My b value is 1/2, seeing as that's in between 0 and 1. This is a decay. Our decay factor is 1/2, or if you feel more comfortable, you can say 0.5, whatever works for you. What's our percent change? What would I notice is going to happen to my y values with each increase in x? Well, it's a decay, so 1 minus r gives me 0.5. What does that r have to be? Well, 1 minus, 0.5. Whoops. So we'll say r equals 0.5. Okay, so again, all I did was I solved for r there. I did it in my head. You're absolutely more than welcome to do it by hand. So with our r value being 0.5, I'm going to multiply that by 100 to turn it into a percentage, and I get 50%. Now, since this is decay, this is a 50% decrease. So with each increase in x, my y value is going to decrease by 50% each time. It's going to be cut in half. All right, looking at number 4, y equals 5 times 2 raised to the power of x. My b value here is 2, which means it's a growth. My growth factor is 2. It's the actual b value itself. My percent change, well, 1 plus r is how I got 2. Okay, so solving for r, I get 1. Now let's turn that into a percentage. So 1 times 100 gives me 100%. So there's 100% growth, or a 100% increase each time. So as my x values increase, my y values increase by 100%. They're going to double each time. Looking at number 5, y equals 0.7 raised to the power of x. Don't be fooled. This 0.7, sorry, I think I said 0.5. 0.7. This 0.7 right here is actually your b value because it is the constant that's attached to the exponent of x. So therefore it is your b value. Seeing that it's 0.7, which is between 0 and 1, this is a decay. I'm going to write that down here. What is my percent change? How are my y values changing with each increase in x? Well, let's see. All right, so 1 minus r, what did I subtract from 1 to get 0.7? Oh, I subtracted 0.3. Now, sorry, I put the 0.70. You obviously did not need that 0 there. Alrighty, so 0.3 or 0.30 times 100 gives us 30%. Now, seeing as this is a decay, it's a 30% decrease, which means with each increase in x, my y values decrease by 30%. All right, last but not least with number 6, 2.3 is my b value. Seeing that it's bigger than 1, it's a growth. My growth factor, 2.3, again, I'm just rewriting what b is there. What is my percent change? How are my y values changing with each increase in x? Well, let's see. 1 plus r, because this is a growth, I'm going to add r this time, gives us 2.3. So what did I add to 1 to get 2.3? I added 1.3. Making that into a percentage. 1.3 times 100 is 130%. So this is an increase. Therefore, with each increase in x, my y value is going to increase by 130% each time. All right, so that's it for notes number 1. We'll be on to notes number 2 tomorrow with exponential functions.